Code, yeah. So after doing the algorithm analysis, we're going to get back to more code stuff, but it's not code stuff yet. It's going to be, well, what's the data structure? The next data structure we're going to talk about, the ADT, abstract data type, is going to be a queue. And you all know what a queue is. You've all stood in a line before. Did anyone go to Starbucks this morning? What? Did you stand in line? You're an expert. You know what you're doing. Anyone stand in a line recently anywhere? In general, it's first come, first serve, right? And if someone's there before you, you stand behind them. Obviously, there's assholes who can jump the line, but that's not going to happen here. So queue, first come, first serve. Or we'll call it first in, first out, FIFO, right? Remember what we called the stack? LIFO. Last in was the first out. The thing on top comes off, right? The last thing added would be the first thing removed. Well, this isn't like that at all. This is the first thing added is at the front. If I had a queue and 10 things appeared, the one that showed up first would be at the front of the queue. You all know how this works. So, there we go. A bunch of people standing in a line. Great. Someone new shows up. They go to the back of the line. I realize how silly this is, showing you this, but yes. And then the person at the front, they're the next serve, right? Does this look familiar for you who went to Starbucks this morning? Yeah? It looks something like this? Great. Maybe I should have a little coffee in his hand. I don't know. So what operators? When I say operators, I mean the methods, right? Obviously, we're speaking more generally. When we talk about a queue, we're not talking about Java. We're talking about an abstract data type. So for the stack, we had like push, pop, and peek. Is empty in size. And so is empty in size, those are going to be very general. They're going to be on like all our data structures. We want to know if a stack is empty. We want to know its size. But for all these data structures, we also want a way to add and remove. With a stack, it's push and pop. With a queue, we often call it in queue and dequeue. When you go into the queue, you in queue, not with an I, with an E, NQ. And when you leave, you dequeue, right? And then there's the same thing as peek. Remember peek? It was look at the thing on top of the stack, but leave it alone. Because remember, the whole idea with these simple data structures is every time you add and remove, the thing exists and then it gets, like you add it and then it's returned, right? In more general data structures, that's not always the thing that we're going to have. But with the stack, add, remove, but maybe we want to look at the thing but not actually remove it. And that's called first. So in queue is add an element to the collection. The element added will be the new rear of the queue, the new end. Dequeue, it removes an element from the collection. The removed element will be from the front of the queue. The element after the removed element will now be the new front of the queue, assuming it exists. There could be a queue with only one thing in it. And if the one thing leaves, well, it's empty now. And the element removed is returned. And then first is return the element at the front of the queue, but leave it in the queue. Calling first does not alter the queue. This does not change its state in any way. It's just an observation of what's going on. Note, it is against the definition of a queue to access anything from anywhere other than the front of the queue. And this was the same thing we had with the stack. It is against the rules to add and remove anything from anywhere else in the stack. And then some asshole in the room is going to say, but what if I want to? Then I say, oh, great, you don't want to use a queue then. No, but I want to use a queue and remove from the, that's a list. That's not a queue. So you could do that. But remember, we are defining what a queue is right now. It's already defined fine. You go to Wikipedia, you'll find an article on queues. It's already got its definition. But this is the definition. And to be a queue, this must be how it works. If this isn't how it works, fine, but it's not a queue. Warning. Now, this is just a Java thing. And Java is actually a little kind of peculiar here. You can actually go and use, we're building these data structures, right? But these data structures already exist inside your programming languages. Your programming languages' standard libraries often have these common data structures. If at any point you're saying, well, why are we building them? Why don't we just use them? Because remember, we're taking a course on how to make data structures. So that's why we don't just, if you're taking a course on how to build a car, you don't just go buy a car. You learn how to build the car. So we're learning how to build the car. If you go and actually look at Java's queue interface, because it does exist, they actually use some different names. What do they use? Add, remove, and element are going to be your in-queue, dequeue, and like first. Okay? They don't actually call it push, pop, and peek. But you'll also notice offer, pull, and peek. Sorry, I said in-queue, dequeue, and first. Pardon me. They also have another set of three, offer, pull, and peek, which is basically the same idea as like adding something, removing something, and observing, but leaving it alone. But you'll notice that, like, well, why do they actually have like two different versions of the exact same like idea? Well, first of all, why do they use different names? And for that, I don't know. Java messed this one up. I don't know what they were doing. I'm sure someone has a reason as to why they went with the non-traditional names of in-queue, dequeue, and first. Pardon?
The second set kind of makes sense in terms of why, because they don't throw exceptions.
Well, fine. Yeah. The wording of that.
You're not like forcing it to add it, right?
Yeah.
If you throw an exception or if you're peeking, you're just looking at it.
Yeah.
You pull it. I don't really know how to explain that.
Well, it's like polling something. Like, hey, I can do a poll.
And then you can just refuse to answer, I guess.
Yeah. Now, I'm guessing add and remove are used because those are the more general words that you use for a collection. So they're following the general collection interface of Java's. But it is non-traditional words used for a queue. But also, yeah, the other question you might ask gets to what you were pointing out is there's actually two different sets of the same idea. Add, remove, and observe have two different sets of those methods. Why? Well, the first set, if you use them and there's an issue, it'll throw an exception. The other set just won't throw exceptions. It'll just carry on as if nothing has happened. This isn't that uncommon. It's not uncommon to have two sets. I'm not saying it is common, but it's not that uncommon in collections to have two different versions of a method, one where it would throw an exception and one where it just fails quietly. You might actually remember there was an example of this that we did briefly talk about in 161. Does anyone remember? It was when we were talking about sets in 161, but it doesn't matter at all. It was a footnote to a footnote in a lecture last semester. Anyways, the names in-queue, dequeue, and first are used here because they are typically what you use. And because we all think Wikipedia is the end-all, be-all, you go to Wikipedia, you'll see it's called, come on, yeah, in-queue, dequeue, right? It is what it is. Cool. Any questions about this general idea so far? It may feel like I'm really, hitting this really hard for a goddamn line, but whatever. I just want to make sure we hit it. So example uses of a queue. This is stupid. We could come up with probably an insanely large list right now. But for the fun of it, we're going to use a very contrived example to show you, well, here I'm using a queue for some computational reason. As a note for assignment 3, you will be using a queue to solve the maze. But it won't be a standard queue that we're talking about right now, where it's going to be a priority queue, which is a little different. Things are removed from the queue based on a priority value, not based on, like, they were the first thing there. But you'll learn all about that when you start doing the assignment. So, rotating cipher. All right? Anyone here have like a Caesar cipher before? You ever play that little thing? You get that little, like, those dials as a kid. You make two like circles, one bigger than the other with the different letters, and you just shift. Exactly, right? Oh, you can encode any message by taking each letter, and if the cipher's offset is 3, you turn all A's to B, C, D's, all B's to E's, all C's to F's, and so on. And when you get to Z, you would actually just rotate it to B. Wait, Z, A, B, C. Yeah, you just loop back around. So think of it like a circle, right? All the letters on a circle, and you just move down 3. Now, the choice to move down 3 is entirely arbitrary. We can move down as far as we want. I mean, how many letters are there? 26, right? I ask every year because every year I always say like 23 or something stupid. There's 26, right? A, B, C, D. Okay, yeah. So presumably, how many rotations do we have? Well, we could do 20, yeah, 25, I guess, because 26 would just be, yeah. I think so. You know what? Let's not worry about that. Counting is hard. Now, someone might be like, well, really, it's only 13 because going 25 one way is the same as going backwards 1 the other way. You're right, but it's still 26, right? Or 25, right? So that's the idea of a cipher. And it's kind of fun to think about this, right? We have a message that we want to encode. All right? So we have an encoding process. So we encode the message, and then we get a code, an encoded message, whatever you want to call it, right? That would be the original string. Like if I took hello and did the encoding on it, I would have a word that's not hello. But then I can just simply undo it by, if I said, okay, take every letter and move it down 3, well, I could undo it by, I could decode that message by just going backwards, doing the inverse, right? That's the idea. The problem with the Caesar cipher is it's stupidly easy to break, right? If you're looking at a message and you have an idea that it's like a Caesar cipher, yeah, at worst you try, or let's try rotating it by 1 on like the first word. No, 2, no, 3, no, 4, no, 5. Ah, there it is, 5, right? It's just, you can hack it away. There is a fixed constant number of things you'd have to try. So it's too easy to decode. The problem is we want it to be harder to decode then. So how do we do that? Well, we can use a rotating cipher, where what if we don't move every letter by 5? What if we remove the first letter by, what if we move like a letter by 5 and then the next letter by 2 and then the next letter by 17 and then the next letter by 4 and then the next letter by, right? That would be a lot harder to decode, or to crack at least. So there's an idea. That's called a rotating cipher. Now, how do we implement that? Well, here's what we could do, right? First of all, understand that if I had the rotating cipher and I gave it to you, you could still do the decoding. You just have to follow the order, right? So the trick to doing the encoding and decoding easily is to have the rotating cipher. So we can do a rotating cipher with a Q pretty easily. What you do is, what if I want to use this rotating cipher, 317425, and I'm just going to constantly, like this rotating cipher, you might look at that and say like 1, 2, 3, 4, 5, 6, that'll only work for 6-letter strings. No. What we do is we move the first letter by 3, then the next one by 1, then the next one by 7, then the next one by 4, then the next one by 2, then the next one by 5, then the next one by 3, and then the next one by 1, then 7. We just keep looping. We'll just keep doing it over and over and over again. So it'll work for any arbitrarily length string. I just keep applying the same thing. So whenever we have this like cyclical process, a queue is fantastic. Because what we do is you take the first letter. So here's an example of an encoded message that I want to decode. Right? So I'm doing the inverse now, I guess. But the direction is arbitrary. It doesn't matter. What I do is I take the first letter and then I dequeue. I'll put my rotating cipher into a queue. I dequeue from the queue. Look at that number. and apply it to the first letter. And then I put that letter back into the queue. I in-queue it. But it goes to the end. Everything else has to go before that gets back to the front. So a queue is really handy. Obviously, I'm not talking just about ciphers. This is a silly little contrived example, right? It's a little game for kids. I'm talking about situations where you have this like looping thing. So we're actually using the queue. So you all have lined up in queues before. So you might be thinking, okay, a queue is great if you're ever like buffering something, right? Something needs to come in, but it can't be served yet, so it has to wait, and then it's its turn, right? Line up at the grocery store. It's a buffer, okay? But now this is a little different. This is like the cyclical process. You just go back. It's like kids on a slide, right? They take their turn, they climb up, they go down the slide, they go to the back of the line. Now it's this like looping process in a queue. There, it's great. Another great application of a queue that may not have been as naturally obvious to think, okay, it's repeating. But yeah, whenever you have anything repeating like this in this like cyclical nature, a queue is fantastic. Is the audio working? Good. All right, yeah. All right, cool. So now let's talk about, okay, any questions about anything so far? All right, so what's the interface look like? Well, if you were to go and download the interface from the course website, these are the methods you would see inside the queue. Public interface queue, and then those are the methods. But again, they're only abstract methods. They're not actually implemented. It's just the return type, the name of the method, and its arguments. If you go download the actual queue interface, though, there'll be the java.comments on each of them. I've just excluded them here because it's very verbose. But that's what we want to have. In queue, dequeue, first is empty, and size. If we ever implement a method, if we ever want to make a queue, and we implement the queue interface, it has to have those methods. And if it does, it's a queue as far as Java is concerned. Remember, with Java, there's no guarantee it's correct. It just guarantees that the methods that have to be there are there. And again, with the interface is there to define what a queue is. It's not there to actually implement it. It's just to say, what is the queue? Not how does it do its thing. No. It's what is a queue. So the interface is how we define what a queue is. Well, now let's go on and implement a queue. That'll be the next topic. And this time, unlike the stack where we first implemented the stack with an array, then we did the link structure. This time we'll start with the link structure. So we're going to implement a queue with a linked structure, a series of nodes. So given the definition of a queue, how can we implement it? Well, we separate the what from the how. We've got the what. Now we need the how. And what do we need? Well, we need a container, a place to actually store the data. That's going to be the sequence of nodes. We need a way to keep track of the front of the queue. Well, that'll just be a reference variable to the node at the beginning of the queue. We need a way to keep track of the rear of the queue. Well, that'll just be, let's just have another reference variable that's always referencing the node at the other end of the queue, at the other end of the link structure. And we need a way to keep track of the size, fine, an integer variable, an integer field for our class to just increment and decrement as we add and remove. That's all we need. But of course, there's still implementation details. Because remember with the stack, we only needed one reference variable, referencing the top. And then the top node always referenced the node like below it in the stack, right? So the top node, and then it had a reference to its subsequent node all the way down to the bottom until the bottom of the stack. So we have to decide, okay, how do we actually want this queue to be like oriented, right? We've got a link structure. Where should the front of the queue be and the tail of the queue, right? Because each node has like a direction. We can only go one way. So if I have a series of nodes starting over here that references this node, that references this node, that references this node, should this be the front or should this be the tail? Should this be the front or the tail? Well, I mean, we could do it any way we want, but to me, it's going to be a lot easier, a hell of a lot easier, if we always have the front, like the actual beginning of the link structure, be the front of the queue. Because whenever we dequeue, that's just removing from the front of a link structure, which was really easy. That was like the easiest implementation of anything with the link structure there is, right? Just set the front reference variable to reference the fronts next there. And then if we have a reference variable to the tail, right? Imagine I've got this big long link structure of who knows how long, it doesn't matter. Just all the way down to the end, I've got the final node and I have a reference to it. It's called the tail. If I ever want to in-queue anything, well, I say tail, your next is the new queue. And then tail, reference tail's next. And then it just, instead of pointing here, it points there. Does anyone have any whiteboard markers on them by chance? I keep forgetting to grab new ones. And mine have vanished. I don't know why. We're missing the guy with them. There's one here. All right. Let's see. Come on. Oh, look at that. All right. So let me draw what I mean, just to make sure we've got our heads wrapped around it. If it didn't work, I would have just used paint, but whatever. I'll call this F for front. And we'll do rear. You can see that reasonably well at the back and everything? So that's my queue. It's not a very big queue. It's a queue. The front, if I want to dequeue something, we're going to need the extra stuff for like, okay, you know, have a reference variable to this so we can return it later. But let's think of the actual removing from the front of a queue. Just say, hey, front, because remember, front's a reference variable to this node. So we say front's next. Well, that's this one. So front, you equal, you're next. And then it'll go, okay, well, front's next is this. So front will just point to this now. Right? And then if nothing's referencing this anymore, what happens to it? It's gone. Right? So there we go, great. Now, if I want to in-queue something, okay, well, I've got a new node. I say, hey, rear, your next is the new node. All right? But we're not done. Sure, the link structure has a new thing at the end of it, but we need to update this reference variable to the thing that's always supposed to be referencing the last thing. Well, that's just going to be the same code. Rear, you equal your current next. So rear, what's your next? It's that one. Okay, well, you reference that now. There. Removing and adding, dequeuing and in-queuing to a queue with the linked structure implementation as the container. Any questions about that? What happens if we do have some edge cases to deal with? What happens if the queue is empty? I'm having them both point to a dot. The dot's there to represent null. There's no actual nodes here. And I want to in-queue. It's a little different, right? The in-queue before, the general in-queue was, okay, hey, rear, set your next to the new node. If I were to do that, I'd get a null pointer exception. It would say, well, rear's null, you can't do that. So that's obviously a little special. If it's empty, we got to do something a little different. And what about this particular situation? What if we have a queue with one thing in it, such that front and rear happen to be referencing the same node? if we in-queue, let's think about the in-queue for a second. In in-queue, okay, rear, okay, the new node, and then rear equals rear.next. So updating the rear is fine. In-queuing to a queue with one thing in it is not too bad. It seems like it's going to be fine. But what happens if we dequeue? Well, what is the code for dequeue is front equals front's next. So we just say front u equal, I'm just going to, the next, which is fine. Right? Because front now references null, the queue is empty. But what references this node? Rear. That doesn't make any sense, does it? It's not the rear anymore. So if we ever dequeue such that the queue is now empty, we got to be careful. Because this node shouldn't be there. Now, I will say, depending on how we actually implement it, this peculiar case could end up not actually mattering. But do you think I would think that's good code? If you wrote code such that the whole class is functionally correct, but you can have a state where this is what's going on, think of it this way.
Yeah, you can do it like you dequeue and it's empty, so you have the size set to 0.
Exactly.
Right? So then when you enqueue,
It's like, oh.
You just set the front and rear to that new node.
Exactly. So in queuing to an empty one is make a new node and have both front and rear reference it. So here if I say the size of this queue should be 0, despite the fact that rear, it's got this like dangling situation of, well, it still references something that's not really there, but it doesn't really matter because rear isn't really there, so the size is 0. Because we dequeued, we decrement size, so the size went from 1 to 0. So is empty, it'll be true. If it's empty, well, in queuing to an empty queue is make a new node, have front and rear reference the new node. Done. That would immediately resolve this situation on the next in queue. But it's still weird to leave your code in such a way that your program could be in this like invalid state. The invalid state is hidden. People using your code would never really know. But when you draw it on a whiteboard, it's stinky, isn't it? So in this situation, if it's ever empty, I usually would very strongly suggest, if it's ever empty, set rear to just be null. So then the garbage collector can come along and actually get rid of that thing. If it's not there, it's not there. It's the same idea as when we popped from a stack, when we popped from an array stack. Remember how we take the thing at top minus 1, and we returned it, and then we decrease top. So top is an integer that corresponds to the next available spot in my stack. But there's some data in that spot, but it doesn't matter because the next time we push something on the stack, it gets immediately overwritten, so it doesn't really matter. But I was like, let's set it to null. If the data is not supposed to be there, it's not supposed to be there. Get rid of it. Someone could say it's less efficient though, because you are adding extra instructions, but code is not for computers. It's for humans. So make your intentions clear with your code. I think being very explicit in having your code get rid of that thing by updating the rear reference variable to be null in the situation where it really shouldn't be there, in the same way that getting rid of the thing from the stack when you popped it, if that's your intention, make your code reflect your intentions. Make your code as obvious as possible to any other programmer looking at your code. Was this rant clear? Maybe if it wasn't entirely clear, hopefully as we go, I'm pretty sure I walk through this example in the code. So we'll see it, but if at any point you have questions, or if you have questions, I'll stop for a second. Ask questions. Pardon?
It is of the preference, though, technically.
What I would say is, functionally, if it's implemented well, with what we were just talking about, you suggested is empty, yeah, you check, okay. If it's implemented well, it's functionally, I would never know the difference. I wouldn't say it is preference, but that to me has a suggestion that like, well, it doesn't really matter. One's not really better than the other. But I would very strongly suggest that one way is better than the other.
So like we do that, we DQ, front's equal to null. So then after we do that, we can say, I guess we have two options. We check if size is now 0 or if front is equal to null, just set rear to front.
What I like about doing it the way where we update rear to be null when it shouldn't be there, when it's empty, is if I have the isEmpty method, I could say is size 0. Or I could say are front and rear null. Like both would work. Actually, all three would work. Is front null, is rear null, is size 0. So when like more things about this, when the state of what is actually like physically going on, I know it's kind of funny to say when I say like physically and you're like, it's virtually, because literally it's just, remember there's literally physical differences, high and low voltages that represent the zeros and ones configured with the transistors on your computer. There is physically a difference. Have the physical configuration of what it means reflect reality as much as possible. There we go. There we go. All right. So here we go. Here's how we can think of it. All the drawings I had before, I just focused on the linked structure. I drew them as circles. Here they're drawn as little rectangles separated with the reference to the data and a reference to the next. I ignored the data. I didn't care. But here's how we can represent it. We have a Q reference variable that references the Q data structure. The Q data structure has a reference to the rear, a reference to the front, and an integer field size. Notice that like in reality, with how everything is in Java and memory, the actual link structure, the nodes, aren't actually like in the Q class. The references to the nodes that are somewhere else on your computer, the references to those are in the Q class, or the Q object, but not the actual nodes themselves. It doesn't really matter, but I always find that kind of interesting. And you know, when you think about that, when you have like references and whatnot, if you have things referencing things, referencing things, referencing things, think of it for a second. Each of those boxes, the light blue, blue, gray, black, those boxes that represent some arbitrary data, those data could be objects that have references to reference. There could be references everywhere, all over the place. And if we were to think of these things as references, like very concretely, not at the abstract level of this, it would be a nightmare. All the more reason to keep your code as like clean as possible, because it might, I've been making a really big effort to give you like good quality code, but I could give you really shitty quality code that's functionally equivalent. The problem is, if you don't get a chance to see shitty code, you don't know what shitty code is. If you're used to only looking at good quality code, you might not see the importance of the good quality code to compare it to the shitty code. Yeah.
I can kind of attest that. Well, like, I won't call my own code shitty, but when I write an assignment and then like before I submit it, I want to look it over again and trying to read it and understand what I did. Sometimes I'm sitting there thinking,
yeah, I know, right?
It works, but like I'm trying to understand it.
Here's something you all should do. And there's no way look, I realize if there's no marks, why would you do it, right? But remember, the point of doing these assignments are not the marks, okay? I don't give a shit about your grades on the assignments. I do in a certain capacity, of course. I want everyone to do well. I want everyone to understand. But the grades aren't what the assignments are about. Students tend to kind of miss the point. Hopefully you don't, because I've trained you well. You're all good students, right? The point of an assignment is to do something. Get your hands dirty and practice and do it. I don't know if you know this, these assignments are kind of tricky because I want you to have a challenge, but you can all do it. I know you can do it. And you can solve these problems. The point of the assignment is you do the stuff that we've been talking about so you can learn it better. Oh, and you get grades as a reflection of how well you did it. That's the point. It's not about getting the grades, it's about doing it to learn it. Oh, and you get grades to let you know as a reflection of how well you did what you were asked. So on that vein of doing the assignment for learning purposes, what you all really should be doing, and I cannot stress how important this actually is, the amount you will gain from the following is way more than I think any of you really get, is you do a refactor of your code. You finish your assignment, you get it working. Because I know that's your priority when you're working on the assignments. Get it working. And then it's working, it passed all the tests, great. But how many of you have done exactly what you just said? You're like, okay, great, I'm going to go look at the code. Oh, Jesus. Ugh. But it works, so I'm happy, submit, good. It passed all the tests. But it's shitty code. That's normal. It's not going to be good the first time, especially when you're working this shit out. I don't care if you're a brand new programmer or an experienced programmer. When you're working out ideas and you're hacking code away to get it working, it's never going to be good quality code. It's going to be trash. Always. So that's when you do a refactor. That's when you go and you're like, okay, let's clean this up. Not just variable names, but the logic. Oh, that whole thing, I guess I could simplify that. That's when you take the time to make your code more like code is for humans, not computers, right? That's where that mentality can come through. And the amount you will gain, like the amount of learning you will get from that has been demonstrated to be like insanely high. So I strongly suggest, and I'm not saying this for the marker's sake, the marker will be happy if your code's easier to follow, don't get me wrong. But really, your refactoring of your code is really important because one, it'll help you understand it, you'll learn more. But two, if you continue programming, if you get a job where you're writing code, you're going to be doing it. The first time you submit a pull request, where you submit your code to your colleagues, and they say like, yeah, this is shit, rewrite it. If that's the first time that you're like, if you've never done it before, you're going to be like, oh my God, they just said my code is shit. It's like, did you not know? But it's not you, it's everybody's is going to be trash. It works on my machine, yeah. It's going to be trash. If the first time that your pull request they give you, they're like, okay, yeah, I'm not accepting this, go make it nicer. If that's the first time you're told to do that, something's gone seriously wrong. You should be doing this. You should be expected to be expecting to do that. Rant over. Any questions about that rant? Refactor your code, make it nice. Get used to looking at your terrible code because other people are going to give you a lot of terrible code too. That's another big part of the job. If you're a programmer, your job isn't to just write code. Your job is to look at other programmers' code. Like I just said, you submit your code, you want to add it to whatever you're working on. Every time a colleague wants to do the same thing, it's your job to do the code review. And they're going to have garbage code. The more experienced they are, hopefully they've already gone and done the refactors themselves. But get used to looking at garbage codes. You might as well start by looking at yourself. To be clear, the code every year, every single year for this course, I go and I refine my code. At this stage, it's been a number of years, so not much is changing. But every year there'll be some changes. Actually, this year there were some significant changes. I actually made some big changes from this year to last year. And it really messed up the TA on the first assignment marking because I gave them like an older version and it didn't work at all with it was a nightmare. I messed up. But Every year I'm always making changes. It's normal. It's what you do. Code is living. It needs maintaining forever. In other words, go keep your assignment 2 beautiful forever. All right. Yeah, any questions about that? Hopefully that was inspiring. Okay, so Q, here we go. If we in-Q something, well, we update the rear reference variable to be that new thing, and size increases. If we DQ, we update the front reference variable, we decrease the size. That's the general idea, but we do have some funny edge cases. What happens when, what would it look like when the linked queue is empty? Well, we already kind of talked about that. What would it look like if there's only one element in it, right? When it's empty, they reference null. When there's only one thing in it, front and rear reference the same node. But those are the edge cases. Every other case is the general case of front references some arbitrary node and rear references some other node. But we got to be careful with the edge cases. So let's start thinking, what would this class look like? Well, okay, a public class, linked queue, T, it's generic. We want it to be generic. Implements Q, which is generic. We implement Q because we want this to be a queue. We've got 3 fields. Front, rear, and size. Size is the easy one. It's just some integer that keeps track of the size. But front and rear are going to be references to nodes of some generic type. Because remember, the nodes aren't the data structure. The queue is the data structure, but we're using the nodes in the same way that we use an array. It's just some container, some place to put data. So far, so good? We've got one constructor. Whenever we make a new queue, it should probably be empty. So you want to make a queue, front is null, rear is null, size is 0. There's our constructor. So now all we have to do is in-queue, dequeue, size is empty. And we're going to want like our toString and equals, right? Our general stuff there. So in-queue. This is actually an example of some code that's changed a few times over the years. And this particular way I've presented it, I think, is the easiest to understand. But if I told you to go write an in-queue with the ideas I gave you without showing you what the in-queue should be, if I told you to go write it, you all could do it. You could all figure it out. I know you could. Like what I mean is if I told you to go implement the queue class, if I didn't give it to you, but I told you to go implement it yourself, you could do it. But chances are your in-queue would be a little uglier than that because you're trying to catch all those edge cases. And the way it's written here, I think it's kind of nice. But let's talk through it. And I've added comments there too, just in case. So when we in-queue something, we call in-queue, and the parameter that it gets, the value it gets is going to be something of type T. Remember, in-queue doesn't take a node. No. It takes something of type T. The queue class is dealing with the nodes. If I'm using the queue class, I just want to give it the thing of type T. It's a queue of type T. If I have a queue of strings, I want to give it a string to in-queue. So immediately we make a node with the element in it. Okay, great. So now we have a node with the thing I want to add. And it's got to go to the rear. But I've got a couple of checks here. If it's empty, front equals the thing we're going to in-queue. Right? If it's empty, well, the front is going to be referencing that node that we just added. If it's not empty, we say rear dot set next to in-queue. Right? That means that's like what we had. Let me just draw it again. What are we doing for time? If this is rear, this is just, who cares, right? Rear. So we've got the is empty, we just set front to be in queue. And if you're saying like, yeah, but you didn't update the rear, shouldn't rear, just wait. If it's not empty, rear, set your next to the thing that we want to add. Okay, great. But this is the state. But either way, whether it was empty before and front got added to, front just was referencing the thing we're in queuing, or we added it to the end. Either way, rear will equal the thing that we just added. I didn't even actually have to say rear equals rear's next. No. I've got a reference to a node called 2 in Q. That's the thing I want in Q. So either way, rear, so will be like TE, 2 in Q. Rear will always, no matter what, will always reference the thing that we just added. Makes sense, right? If we just added something, the thing we're adding is in the node 2 in Q. The thing we just in-queued, that's the new rear. Whether it's the only element in the queue or not, it's the rear. So this was this case. Okay, imagine we had an empty queue. Front, rear are both referencing null. And then I say, oh, okay, so this is the isEmpty case. Front is 2 in Q. Oh, okay, well, TE is that one. So front equals 2 in Q. It's not empty. Rear equals 2 in Q. Oh, okay, well, that's just going to be... that's what we wanted. An empty queue, we add one thing to it. It's a queue with one thing in it now. And front and rear both reference the same thing. Increase size, once we're done, we added something. And then return true. Return true because generally in Java, your collections, when you add something, it returns a Boolean on the success failure of it. Now, we didn't have to deal with the other edge case. What happens if you in-queue with what happens if you dequeue with a queue with only one element in it, right? That funny thing, what do we do with the rear reference? Well, we'll see that tomorrow when we start talking about dequeue. Any questions about what we just saw, though? Yes?
When you have a single element in a queue, you still have rear reference at all?
No, front and rear both reference the same thing. The node can be both the beginning and end of the queue.
Okay. But in terms of like functionality, would it not really matter if rear is still referenced?
Well, my in-queue is, if it's not empty, rear.set next to in-queue. If rear is still referencing null, that's going to be a null pointer exception. We could implement it other ways where you could maybe make that work, but I think it would just make it more complex. Yeah. All right, I'll see you all later.